This video is published under the Creative Commons license BY and CSA, which means attribution, non-commercial and share-alike. Third-party material has been used for which the permission is specified explicitly for every diagram, photograph or whatever has been used. Please mention the author as Andreas Pfennig, Products, Environment and Processes, Department of Chemical Engineering, Université de Liège, Belgium. A disclaimer applies. Welcome back to this video series on thermal unit operations. We are still in the section on general considerations, and in this video I would like to show you an example of how one can apply that in the step construction for a given slightly more complex example, as we saw for distillation when we derived originally the McCabe-Thiele diagram. Before that, I would like to remind us, so to speak, of different things. On the one hand side, the possibilities that we have for which we can use this method. On the one hand side, we have seen we can use it on a mass basis or we can use it on a molar basis. So both is possible. Often the thermodynamic equilibrium is described on a molar basis, and if you want to apply the mass-based description, which is equally possible, the balance is identical, the lines are in principle identical, but you have to be consistent. So in that case, if you want to do this on a mass basis, you need to describe your equilibrium on a mass basis as well. And then there are two situations where it can be applied. On the one hand side, you can regard, so to speak, the total flux, if the total flux is constant, which means that you have an equal countertransport, so an equal molar countertransport. Equimolar evaporation and condensation was one of the examples. Or equal mass countertransport, depending where you are, so to speak, if you want to apply this or that. In that case, where you use a total flux, you use fractional compositions in a binary system. So mole fraction or weight fraction, depending again if you are on mass or on a molar basis, and you apply that for a binary system. It says a pseudo-binary system because in some cases you are able to combine some components that behave quite similarly as one component and then nevertheless be able to treat that as a quasi-binary system, as a so-called pseudo-binary system. The other option is, well, I should say, this is mostly for rectification. It's the famous case, so to speak, whereas the other option that we have mostly applies to solvent extraction or absorption. Because there we have carrier flow rates, we have a liquid and a gas stream. They are generated from, not by evaporation, the vapor is produced by evaporating the liquid, and the liquid is produced by condensing the vapor. Here you actually have two dedicated carrier phases that are moving in countercurrent fashion through your process, and there is a transfer component being transferred from one phase to the other, extraction, absorption or desorption, as an example. Here we want to assume that, or need to assume that the carrier flow rates are constant and that a transfer component is being transferred between these two carriers. Again, we can do that in mass or molar considerations, but now we relate, so to speak, the amount or the mass of the transfer component to the amount or the mass of the carrier component, which leads to loads, mass or molar ratios, how that is also called in the literature. Then finally, we realize that we of course have a ternary system. So we have our transfer component, our two carrier flow rates, two carrier components correspondingly, which means we are in a ternary system. And again, we can regard that as a pseudo-ternary system if there are more components that behave in a similar way. Actually, in this case, you can also regard a variety of individual components separately if they don't influence each other. In that case, you are able, so to speak, to set up this operating line diagram for each individual component. Of course, you always have the same equipment, so the same number of theoretical stages, which defines, so to speak, the separation efficiency that you can reach for your different components. So the number of stages is always the same if you have, even if you regard separate components independently of each other, different transfer components independently of each other. That's one thing we want to remember, and it's quite important that you have to be consistent. Because, for example, in industry cooperation, we found in one case strange results, and the result was actually, or the point was actually that they used something like this. They wanted to apply that, but didn't use the carrier fluxes, but the overall fluxes, like here. So they mixed these two cases, so to speak. So one should stick here, or there, here, or there and be consistent. Also here one has to say, here we require this equal counter transport, and we have to check where actually is the counter transport equal. So which flux is actually being constant, the mass flux or the molar flux? Typically, if you have the molar enthalpy of evaporation, which is constant, which doesn't depend which is the same for all components, then you are on a molar base. You have to be there. You cannot choose anymore. Yeah, if there is an equal mass counter transport, you can use that, of course. It depends. You have to look. Of course, you can still use the other one, but the accuracy will be less. Okay, so it's one thing we want to remember. The second thing we have already seen in the last video and derived significantly earlier. We have seen that on the one hand side, we then can represent the sections of the individual countercurrent processes by operating lines, where the slope is always the L dot over G dot at that point in the process. And on the other hand side, we have seen that always the two flow rates that meet in a column, in a countercurrent process, generally speaking, mustn't necessarily be a column, that these compositions of these flow rates can be found on such an operating line. So the operating line combines all possible compositions that can possibly meet within a column at a given balance plane. Balances are quite fundamental, so this is always something that you find, and the points you will always find. So there's no way around that. If the assumptions are fulfilled, of course, clearly speaking. So that's the second thing we want to remember, and now we can apply it, and we want to apply it to a slightly more general case than that we have regarded for the deriving originally the McCabe-Thiele diagram for distillation. Well, what do we have? We have a feed, we have a Q which is less than 1, which means we are in a two-phase feed. So this is the XF over Q, this is the intersection line. So we have a two-phase feed. We start out, or we have, for example, a distillate composition that we want to have over here. And, then we have a reflux ratio at the condenser, which leads to this XD over reflux ratio plus 1. So we get this operating line, our rectifying line. And after theoretical stage 2, we want to remove a vapor side, a vapor stream. So here we have a vapor side withdrawal, which leads to a kink in the operating line. So below we have an operating line like that. The slope has to be defined how large this vapor side withdrawal actually is. And, but nevertheless, we are now here. And the slope always will be lower than before. So below it's always lower the slope than above. That is now intersected with the intersection line, with the Q line here. So that defines one point of our stripping line. For the stripping line, the second point is defined by the reboiler conditions. And there we want to heat with saturated vapor, pure water vapor presumably. So we are having an aqueous system. And at XB, so to speak, that's our bottom purity that we want to achieve, or that we achieve due to the balances. So if that is specified, flow rates are specified, then that is typically specified as well just from the balances. Or it's given, depends which way around. Anyway, you get a consistent set of these three compositions. This is our XB. Now, because it is saturated vapor, that has to lie on the x-axis. And so that's our second point of the stripping line. So this is then our stripping line, combining these 2 points. So overall, our operating line is now this. Here's the kink, now this, and then below our stripping line. And of course, we can then do our step construction on top of that, 1, 2, 3. But here you see, by the way, that of course you only, if that is specified like this, that after the second theoretical stage there's this vapor side withdrawal, you first have to draw these 2 stages, and then you are here. Then you can draw this in continue, and then you can draw the remaining steps, and you see that overall you need 7 theoretical stages for the separation between XD and XB. And now you can ask, or have to ask yourself in a second step, so that's just the theoretical stages, that you need to separate the XF into these 2. And the second question now is, well, do I have a total or partial condenser, which means this is possibly my partial condenser, or do I have a partial or total reboiler? So this is possibly my total reboiler. And only the remaining theoretical stages are then to be realized in the separation active part of the distillation column. Well, as I said, typically the condenser is a total condenser, so that is still to be realized. This is not the partial condenser, but here you frequently have a partial reboiler at least, so that corresponds to your reboiler as a frequent case. But as I said, you always have to check individually for the specific case that you have. And with that, we can realize that overall, we have a wide variety of countercurrent processes that can be depicted with some simplifying assumptions, of which we all typically find one set of assumptions that are fulfilled so that we can apply that somehow with some accuracy at least in a simple design diagram leading to a step construction. That step construction is then often called the McCabe-Thiele diagram in the YX diagram that represents the corresponding separation process and that allows us to determine the number of theoretical stages graphically in this case, or, that's I said in the introduction, many videos ago, so to speak, even if you have cases where you do actually the simulation with a corresponding simulation tool, Aspen or whatever, ChemCAD or whatever, not advertising any, in that case you want to depict your result typically also in this in such a diagram, possibly if convergence fails to see what's actually happening, or if convergence works but you get strange results, you plot it and see does it work and directly see what happens in such a diagram. And that's why actually these diagrams are so valuable, even if you are doing the design by a simulation. With that, I would like to thank you for this video, and I hope to see you again in the next video.